In this recording, we'll discuss flat mirrors. Okay, now again, like what we mentioned before, if we have an object that we place in front of a mirror, what's going to happen, every point of the object is going to reflect light in all directions. Some of that light is going to, once it is reflected off the object, is going to travel in a straight line and is going to eventually hit the mirror and be reflected off the mirror. Once it is reflected off the mirror, it's going to be reflected according to the law of reflection. A flat mirror is a smooth surface, so it is specular reflection, and the light is going to be reflected according to the law of reflection, which says that the angle of incidence is equal to the angle of reflection. Part of that light is going to reach our eye, and the light that's going to reach our eye is going to look like it is coming from an object that's just behind the mirror. Our eye is not going to distinguish that these beams actually had to be reflected off something before getting to the eye. All what the eye is going to see is beams that are coming straight to it, and so it's going to, these beams are going to look like originating, continuing the straight line from eye parallel to the beams, originating at a point where the two beams would intersect, and that would be the image of the tip of the object. Okay, now this image, we call it virtual. Virtual. Why do we call it virtual? We call it virtual because it does not exist. Light reflected off the mirror is giving us the illusion that there is an image there. But if we go and place a photographic film, for example, behind the mirror, that film is not going to have an image on it. If we send someone to look behind the mirror, that person is not going to find anything. He's not going to see anything behind the mirror. It's just the light that's being reflected off the mirror that's going to give us the illusion that there is something behind the mirror. That's why we call it virtual. So the opposite to virtual, a real image, we'll discuss that later, but a flat mirror would produce a virtual image. Now, to illustrate some of this, I'm going to run through a few simulations. Okay, I'm going to go to this one. This is quite neat. No, actually, it seems I didn't pull it up, so sorry. So let's go here. I thought I pulled it up, but it seems I did not. Okay, there we are. Okay, so what we have here is an object, a mirror, and then the image. And look here, it allows us, for every part of the object that we choose, it shows the light rays reflected off the object. For example, here it's green reflected off the green eyelashes. And each of these beams, I cannot the minute I put the mouse over it, the simulation changes, but each of these beams is going to be reflected according to the law of reflection, and they are going to look like they are emanating from the point just behind the mirror. And notice here, the ear that's furthest away from the mirror is going to be furthest away in the image. The closest ear is closest, So everything is in exactly same position relative to the object. It's the exact image, the exact position relative to the mirror for every part. What you notice here, the simulation, as I continue doing this, it is showing us we are drawing actually the point here. I'm drawing the blue one in the actual simulation. Okay, here's the yellow, and so on. So my image is exactly identical to the object. Now, how do we determine images if we don't have simulations? So what we do is we draw first a light ray that is perpendicular to the mirror. Now, if it is perpendicular to the mirror, its angle of incidence is 0 and its angle of reflection is 0. So for example, if I'm going to take this, that's one ray. That's perpendicular to the mirror, and the reflected beam is in the same direction. And then we draw a second ray at another angle, theta sub I. That theta sub I, that angle, that light beam, if it's going to make an angle theta sub I with the perpendicular, it's going to be reflected at theta sub I. Now, what you do is you extend both lines towards the back of the mirror. Okay, these two lines, these two reflected beams, they look like they would intersect in the back. And where would they intersect? At the tip of the object. And I can do it for every small part of the object, and that's the way I'm going to reconstruct the image. A little geometry, when you do something like this, if you do it carefully, graphically carefully, you'll find that actually this D is going to be the same as this D. Because the angles are the same, the geometry will show you that we should get the same D, which is telling us that the image is going to be at exactly the same position away from the mirror as the object is. Okay. In other words, the image distance is the same as the object distance for a flat mirror. Now, so again, this is just illustrating that. The image is exactly identical to the object, exactly the same distance away. Now, one important thing, finger here, where's its image? Exactly across from the mirror at the same distance. This finger, same thing. What about the top of the fingers? Top here. Just at exactly the same position away from the mirror as these are. What about the bottom of the hand? The bottom of the hand. In other words, if you notice here, the mirror does not flip images. Does not do anything to the image. It's just the object and image are identical to each other. Okay, relative to us, they might look different, but they are identical to each other. Object and image are the same distance apart from the image. This finger is not going to come to this side or this finger to this side. They are exactly at their exact position relative to the mirror. Neat things that people do. This is from a museum, and probably you have seen it in some other museums. Look at this person here. This person looks like flying, but actually we have a mirror here. And the person is standing with, I'm not sure if it is female or male. I'm not sure I can distinguish it well, but I'm thinking he's a male. But anyway, so positioning the face halfway along the mirror, and then what's happening, you don't notice it very well here, you notice the leg of the person there. So it's standing on the leg, but this other leg is lifted, and by lifting the leg, it's going to appear to the kid or to whoever like that person is flying. This is a little bit even more dramatic, and that's the same thing. She has the mirror between her legs. Her left leg is the other side of the mirror, and she's using it to stand on it, and she's lifting the right leg and doing a little act in here, and what we are seeing here is the image of the right leg. When you have an ambulance, not all of them do that, but some of them do it. Why do they do this? So when we have a rear view mirror, so the A is going to be here, the M is going to be here, so it's going to be at the same place. But then when we are looking at it from the other side, we are going to see it the correct way, and we are going to be able to read it as ambulance. This is another neat thing that you can find in museums. They call it, they have different names for calling it. This is actual a museum display, and this is a way to produce the same kind of thing. They have the instructions on how to build something like that. What you have, according to the instruction, actually a piece of plexiglass here, and two light sources and dimmer switches to control the lights along these. And what you have two people standing behind the mirror. We have in this case this guy and this lady. And what you do, you arrange such that both of your faces are facing each other, and then you start changing the lights on these. So what's going to happen when you change the lights? On the plexiglass, from the front surface, there is going to be light reflected. So if light is going to be reflected, the plexiglass, like any type of glass, is going to act as a mirror. Usually that image is so dim for us to be able to see. But by controlling the amount of light, we can make it a little brighter. And we can control how much from the other side is going to be transmitted by controlling the amount of light. It's a very neat demo, so it shows both images morphing into each other, and that's why they call it freaky faces. This is actually the same kind of idea. You have a piece of glass, behind it a glass of water, and you have the candle here, and when you look at it from this side, it looks like the candle is inside the glass, while one of them is one side of the glass and the other side. So for the candle, it's a reflected image, but the glass, it's actually a transmitted image. One interesting question is usually what is the size of the mirror that we need to use to be able to see ourselves? But before we get to that, let's answer this question. We have a mirror. You can see above your head, but only down to your knees. To see your shoes, what do you need to do? Move closer to the mirror, further from the mirror, or move to another mirror. Okay. Let's try to illustrate the question. If we move the mirror closer, so a light beam from here is going to travel like that. It's going to be the angle that it's going to make with the perpendicular is a larger angle than this one. Now if we make it further away, the same idea. So if I try to make an object from here, it's a bigger angle and we still cannot see it. Come closer here, bigger angle, we still cannot see it. So what we need is actually move the mirror down, otherwise we are not going to be able to see it. Okay, how would you determine if you can see Fido's tail or not? What you do is you take a ray, then you try to draw the reflected ray. This one obviously is not going to make it, so the one that's going to hit the end is the one that will give you the chance. And in this case, it looks like quite high. It looks like you will not be able to see it on the mirror.